Hello and welcome back to Calculus 2, section 6.7 on physics, physical applications. So word problems, we're going to do tons of integration over here, obviously, because it's integration application. Can't even speak anymore. That's it for today. Bye. We're going to do applied problems in physics. There we go, finally. So the first concept we are talking about here is the mass. I like to describe mass as quantification of physical existence. So if you can touch something, lift something, it's there. Presence in mass. It's made out of particles, atoms, and so on. So the mass is this quantity that is there for objects that physically exist. As I said, you have mass. This bottle of water has mass, cell phone has mass, everything has mass, the planet has mass. Love doesn't have mass, right? So it has to be something that it's in our physical world. Now, in the United States, people are used to weight. Now, weight is a mass times acceleration. So to calculate weight, you actually have to take mass and multiply it by gravity in order to find the pounds that are in European units, newtons, right, to metric system, right? So mass is going to be measured in kilograms in SI system of units, which is international system of units, and the mass is measured in, does anyone know, unit of mass? Usually I have someone. Well, grams, kilograms, so that's metric. What is the imperial, the one that it's used in US? No, that's force. That's the weight.
Oh, it's the weird sounding one, but I don't remember what it is.
What's the question?
What is the unit of mass in here in US? Unit of mass. It starts with an S. I'll help you out. Starts with an S. It's not ringing the bell.
Sterling?
Nope.
Sterling.
Sterling. I love that.
Slug.
Slug. Oh, you looked it up. Okay, on the phone. Yes. So it's a slug. It's about 15 kilograms. So,
I don't think it's stone.
no, stone it is a unit still, but it's,
Stone's like 16 pounds.
Yeah, but that's, again, it's not metric. Anyway, but it is a unit of it. It's just different unit. So like you have the temperature, right? You have a Celsius, you have Fahrenheit, Rankine, you have Kelvin. It's nice when someone has asked me, what's going to be, because I hate when people talk to me about weather. I see it. Like there's no reason for you to explain it, because they have nothing else to say, and just like talk about the weather. So it's going to be great weather today. I immediately converted to Kelvin. Just to have a little shred of interesting thing going on. It's like, it's going to be 300 degrees tomorrow. All right. So, it's awesome. Try it. Or if you have to call out of work, your temperature, just send it in Kelvin. Like I have a fever at 300 in Kelvin. It's like, I can't come in. 300. I thought people die at 106. Yeah. All right. So that was an echo. So mass, quantification of physical existence, guys. It depends on density. Denser objects are heavier. That would be me, right? And you can, if they occupy the same volume, the denser objects would be more massive. So the good old trick, what's heavier, pound of feathers or pound of, again, pound is not unit of mass, but pound of feathers or pound of gold or lead, whatever you want to put, right? Pound equals pound, right? Kilogram equals kilogram. So, but the trick is that you need the truckload of feathers, and then you need a little nugget of gold, right? So clearly gold is much denser than a feather, and that density is the one that helps you figure out the formula for mass. Now, this being the Calc 2 and we working only on single integral with either dx or dy, we can't really do a great job with the formula. We have to do some approximation. So let me show you this. First of all, mass is defined as density times the volume. So, as I said, if you have 1 kilogram of feathers and 1 kilogram of gold, it is going to be a huge pile of feathers and just a nugget of some kind of gold, right? So the reason is gold is far more denser than the feathers. Now, the trick is that since we only have access to one integral so far, we can only technically work the length out. One way, we can only talk about the mass of the objects that we can pretty much just take for the length. So if you take a long rod from 0 to L, you can disregard its cross section. Yes, the rod is third-dimensional object, and as a third-dimensional object, it does have 3 dimensions to it. But then when you take a look at the length of the rod, and then you compare that to this very, very tiny cross-section area of the rod, the 0 to L is really overpowering as a dimension, and we can think of this, even though we know it's not, we can think of this as one-dimensional object, because technically the only dimension that is here overpowering everything else is 0 to L, which is length. So I can, in this case, say that rho of x, which is a Greek letter, rho of x is going to be called the density function. And we need the density function because for certain things, objects, density is not uniform. Density of your body is not uniform. Lungs are not dense at all. Muscle is dense, right? So then you compare some people, obviously, right? We all know some people have non-dense brains and others do. So if there is a uniform density would be a number. And then the entire object is made out of the same density material. You take a well-mixed plastic, for instance, and you have a piece of it. Think of a snowball made out of plastic, right? So it's a plastic ball, right? And it's filled with plastic everywhere. And let's say the density of that plastic, we decide it's called number 2, whatever, right? Then this density function just becomes rho equals 2 because it's a constant density. So constant density, uniform density means the entire material is one density. So you can have something made out of gold and only gold, something made out just of iron, or something made out of, right, whatever it is, so the same density throughout. And then you have things that are made out of different materials and different densities of different metals and stuff like that, mixed everything in. So the objects are denser in some place and denser in the other. In that case, we have a variable density, which is why we need rho of x. So if this rod was of a variable density, let's say you have x squared plus 1 density. So let's say the density for this was given as, rho of x is equal to x squared plus 1. Now, this x is telling us that the density will be higher as you go further away on x-axis. See, when x is equal to 0, the density of the rod is 1. And then when you go all the way out to, let's say, L equals 10, the density of the rod will be 101. So the rod will be 101 times denser on the L side than on the 0 side. So with this, you can create any kind of function because obviously different objects in our world have different density properties, and then you have to figure out what kind of function would model that type of density. So I just made up a function here for density, and as you can see, the density on this end will be 1 and 2 and 3 and 4 and 5 and so on. The density on the other end, depending on how large L is, right, would be much higher than the density on the left. Now that means that you can bend this easily on the left and you cannot bend it on the right. Now, being that it's much denser on the right side and less dense on the left side with this particular density function, this means that the center of mass is not going to be in the middle, because this object will be much heavier on the right side because it's much denser on the right side, right? So we are going to use that later on in Calculus 3 to find center of mass for different objects. Calculating center of mass in the design of cars, airplanes, and everything else, ships, right, is extremely important. Center of mass of the building as well. You don't want it to tip over, right? Especially that one that they built in China for Chinese Olympics. Have you seen the Z building? When I saw that building, I said, I don't know how this thing stands. Because you have it's actually a third dimensional, so you have like two Z's, and then the top of the two Z's meet, and when you look from the side, it looks like a Z. It's a really strange building. Maybe I should also look it up, right? You have to have the center of mass worked out so well, because the building like that can fall easily if you screw these things up.
But if it's a Z, the Z is like it's balanced in the sense that you have up the
properties of the material. Look, when you hold a heavy object close to you, it's not heavy. You hold it like this, it's heavy. Remember that the building is made out of steel and concrete, and this Z arm that extends out is carrying a lot of weight. The properties of the materials that hold that one, right? So if you look up at these buildings, you have to figure these things out as well. But, we can just bring it close to home and say, we all understand that we can't drive SUVs the way we drive our cars. Because, why? SUVs are tall, top heavy. Trucks, the same thing. Easy to flip them. They even have the warning right on the visor where the driver is, to say that you cannot drive SUV the way you drive the car because they are top heavy and they flip easy. What's the safest car in the galaxy? Tesla.
The SUV with a roll cage.
SUV with a roll cage. Tesla car has no engine. All of the weight in the car is on the bottom of the car where the heavy battery is. So the car has the lowest center of mass of all cars, and it's virtually impossible to flip. It's impossible to flip Tesla. I mean, obviously, if you make ramps and things, you're gonna flip it, but it's impossible to flip Tesla cornering in the street. You can flip SUV like that, right? Now, the trick is that Tesla would have the orders of magnitude lower center of mass. So calculating these centers of mass, where you balance the objects, is extremely important for mechanical engineering and all your design. And again, the proper formulas for this with double and triple integrals will show up in Calculus 3, and they will build directly off of the formula that we are going to learn right now. The formula that you are learning in Calculus 2 is the formula to calculate mass for the long objects. So technically, even though we say one-dimensional, we know they're three-dimensional, but only one dimension is the one that we care about in this case. So the mass m will be given by the integral from 0 to L, which is the length of the rod, right, of the density function dx. And this would be the mass integral. And as long as you can integrate the function rho, you should be able to find the mass of the object. Now, this is going to later on turn into, looking for the center of mass and so on. You calculate some moment integrals and so on, but that's all for Calc 3. So you will see this formula exactly like this in Calc 3 again, if you're taking Calc 3, obviously. And this formula will be also upgraded to have 2 and 3 integrals inside. Okay, so now, if I have some kind of, I'm just going to go and pick up whatever homework problem to just do this example. We don't really care too much, so I'm going to pick one of the little bit more interesting examples. Again, you're just integrating. So let's say the density rho of x is given as the piecewise function 1 and 1 plus x, and this is on lengths 0 to 2 and 2 to 4. So now you have a 4 meters, 4 meters long rod. 4 meters long rod is twice my height. Pretty much to the ceiling in this room, let's say. If you, can we stuff another one of me on top of me and get to the ceiling?
Yes.
Okay, so now you have the visual of what 4 meters would look like for this particular problem. Now you can see the different density. There is a uniform density of 1 for the first half of the rod, and the second half of the rod from 2 to 4 meters, right, which is from here to the top, is going to have a variable density, which means that the rod is going to get denser and denser and denser as we go higher and higher. So now I have to work 2 integrals together. There will be a mass integral for uniform 1, and then there will be another mass integral for 1 plus x density, and then mass of the first plus the mass of the second would be the mass of the entire rod. So m1 will be the integral 0 to 2 of 1 dx, and that's a simple x 0 to 2, which gives us mass of 2, say 2 kilograms. 2 kilograms is about 5 pounds if you convert it. Again, you're not comparing the same stuff because kilograms are units of mass and the pounds are units of force. But roughly, you would feel them the same way, okay? If you hold 2 kilograms in one hand and 5 pounds in the other hand, they would pretty much be, right, the same weight. And now M2 is the mass 2. We have 2 to 4 now, and we are integrating 1 plus x dx. So that's going to be x plus x squared over 2, computed from 2 to 4. And now we don't have a 0 in a limit, so we have to compute the expression at 4 and then subtract computing expression at 2. So 4 plus 16 over 2 minus 2 minus 4 halves. The minus would distribute, so it would change this plus into a minus, right? Because f of b minus f of a. 16 over 2, so we have 4 plus 8 minus 2 minus 2, which is 8. The total mass is going to be mass 1 plus mass 2, which is 2 plus 8 is going to be 10. And you know what, I'm just going to put in kilograms, right? Generally, it's measured in kilograms. So, 10 kilograms would be the sack of potatoes, the 10 kilograms, or apples or something like that. It can last you for a long time. Because that would be about 40 pounds. Okay? 10 kilograms, about 40 pounds. No, 22 by 2.2. Yeah. So it's going to be about 22 pounds, this 10 kilograms. So that's it, guys. That's all. You learn the formula for mass, and then you plug the density function, which is given, and you compute the integral, and you get the mass. So that's the part one. The next one is work. Another huge concept in physics. And this one is related to energy. So the work done is directly what energy you put into the system. It's the energy that does work. So you can measure it in calories, you can measure it in Newton meters. It's a whole bunch of different ways to measure it. There are different types of energies and so on, kinetic and potential, and a whole bunch of stuff that you will learn in physics. We don't do that stuff here. Obviously, we're just calculating things. So work is force times the distance, right? So work is equal to force times the distance. And obviously, in order for me to move this chair, I have to apply force to it, meaning I have to push it or pull it, and that's the force, and then it will go a certain distance. So now, I literally do work to move this chair out of my way. If I don't want to do that work, I have to jump over it, right? Or go around it. Or maybe I want to do the work and move it out of the way so I can walk that way. One of my friend's father was always walking on the hoods of the car that would go into the crosswalk when they don't get to stop. He would, it was a really, really beefy guy. So he would, as soon as they go into the intersection, he would literally just go and walk across the hood and just walk around and keep walking straight, right? Don't go into the crosswalk on the intersection, right? With the car. Do that in New York, probably get shot, but these are different times. Anyway.
You would walk on the car?
Yeah, he would walk across the hood of your car. If you don't.
How tall was he?
Well,
how did he get on there that fast?
It's not that. The hood of the car is not gonna be.
Yeah, but if I want to go onto the hood of the car.
Well, you have a shorter leg, but you see this?
Oh my God.
It's not a problem, right? Even if you're 6 feet, it's not a problem. And if he's 6'4", anyway.
I'm not 6'4", so that's probably.
And so you technically have like a dinosaur, leave the footprints on the hood on the other side. Next time you make sure you don't pull into the intersection. Anyway, so work is force times distance. You push or pull, or something pushes or pulls. The object will cover the distance, and we call that work. There is energy in the system because force is exerted in newtons, and the force you guys know as pounds, right? So work is also measured in foot-pounds, and you've probably heard that, maybe related to a car or something. So foot-pound, right? Foot-pound, distance is measured in feet, and force is measured in pounds. But we generally say Newton meters for the SI system. Now, calorie is something that you would eat, right? And that's the same thing, right? It's just a different size. And you heard about other energy measurements as well. So now, when you are dealing with work, which is force times the distance, you will take so work is force times distance. This formula here is for a very basic application. You see, force needs to be constant here, and if the force is constant, let's say always 20 newtons or whatever it is, You multiply by the distance and you get the work. But the trick is that the force in the world around us is actually never constant, right? If you want to push a fridge or something that it's heavy, right? You are not going to have a constant force pushing, because remember, there is a situation where your hand made the contact with the surface. There is that split second. Made the contact with the surface, but the strength of the push is still not there, right? And then the big push happens, and then the fridge starts moving, and the fridge is moving, and you're still pushing, and then you're getting tired, so the force is, less and less and less as you're getting more and more tired, right? That's not a constant force, right? I can draw the graph for something like that, and if you take a look at the force as you cover the distance, you can also think of time, right? There is this situation at 0 where you are still not pushing and the fridge didn't cover any distance yet. And then it's going to have this very steep, right? Very steep, because your fridge didn't make a distance yet, you apply the force, right? And very steep, and there's the peak of the force. This is how strong you are, and then you are going to start getting tired, and you're going to use less and less force. So we actually have a variable force, and that variable force will be called f of x, variable force. Now, technically, everything in our world has this variable force. If you hook up a load to your car or your truck, you're pulling a trailer or something, or trains, it's hardest to get going. You know that as well. If you are pulling something, it's always hardest to get going. If you lose electrical power in a house and everything is still connected to the wall, right? The chances are that, well, it's compensated for it, and they have to be very careful. You see, what happens is you lose the power, and the voltage in outlet is 118. When you connect stuff to it, it drops down to 110. So we say 110 in the outlet, but if you measure it, should be about 118. So probably you heard someone sometimes give you the advice to, if you lose power in a house, to disconnect, let's say, at least electronics. Computers, if they're not connected to surge protectors or UPS units, disconnect TV, disconnect if you have a Blu-ray player, a computer, cell phone chargers and stuff like that, right? Disconnect them from the wall. Fridge, not so much, right? Why? Because what happens is, in order for them to restart everything, they have to start at even higher voltage, because right now they have to jumpstart everyone's devices that are not unplugged. Now, that can actually be too much for certain cases, and it can actually fry the computer or fry something, unless you have the surge protector plugged into surge protector or plugged into UPS unit. Obviously, UPS unit is the best because it converts the grid into the battery, and then battery back gives over a computer, so that's guaranteed never to damage your electronics. But then, again, UPS unit is going to cost you money. So, like everything else in life, you trade money for the insurance, security, or whatever else, safety. So, thinking about this, there is always the peak, right, of the force. That it's there, and then it might dwindle down over time, which creates a variable function. And as soon as you don't have this to be constant, we have to go to the integral immediately. So the integral equation that we are learning now for work is that work is equal to the integral a to b, and this is a to b, the distance you're covering, of the variable force times dx. So that would be our integral for work. And if, as I said, if you can model this, or they give you in a text this way, which way the way this goes, you can just plug that function in here, integrate. It's a basic integral from Calc 1, solve that in 2 seconds. Now, the application that we want to learn in this class right now is the application when the spring does the work. Now, you know the spring, sometimes your pen exploded and then a little spring came up and maybe you played with it and then tossed it away, right? The springs are one of the most important parts of mechanical devices. You can find springs anywhere. Spring and rubber bands work the same way. Obviously, springs are far more durable, right? So the spring has the property that it always wants to do opposite of what you want, what you're doing to it. So if you compress the spring wants to push out. If you stretch the spring, it wants to push in. Same thing like rubber band, right? So with the spring, you see, the trick is that as soon as you bother it in any way, whether you stretch it or shrink it, right, you are adding energy to the system, and the spring wants to do what every other object on the planet wants to do, in the universe wants to do, is to go back to the lowest energy state. Lowest energy state is called equilibrium point. Your equilibrium point is what? Lowest energy state. Being passed out, drooling on a pillow. That's the lowest energy point. Then a little bit more effort, sitting on a couch watching TV. That's more effort than sleeping, right? But it's not the lowest energy state, but it's pretty much there, right? You are almost as brain dead watching TV as sleeping because you're dreaming, right? So there is a process here and there, some people would argue that being what's on the TV these days, you're probably more brain dead watching the TV than sleeping, but anyway. So what you do is now observe the spring and understand that as soon as you either stretch it or compress it, it has energy that wants to push the other way, which means the spring can do the work. If the spring is compressed and I add an object to the end and I let go, the spring is going to push that object out. Spring is going to shoot it. So you heard the spring-loaded whatever. Spring-loaded whatever means that when you use that whatever, the spring will be compressed and the spring will release the energy once you let it release the energy, because the spring wants to go back to its natural length when it's in equilibrium in the lowest energy state and it's not bothered, right? So now there is what's called the Hooke's law. So it's a name of a physician, right? Physicist who came up with the so Hooke's law says that the force that the spring exerts is equal to the spring constant K times the X, which is the distance that you compress or stretch the spring. So this is the force, this is the spring constant, and this is the distance of the stretch or compression, whatever, distance of the stretch or compression. So this constant K is very important because that's the one that differentiates between your little pen spring and the one that is in the shock absorber of your car, right? So they look the same. One is bigger than the other, obviously, but they look the same. So what's different for those two of them? Well, K is different for two of them. When you take the spring from the car, right? That's the one that makes your bumpy roads not so bumpy, right? And let's say it's this large. you would not be able to compress it by hand. Where you take the one from your pen and you can play with it all day long, right? What's the difference? The difference is K. The higher the K, right, the stiffer the spring. Harder to compress. Do we find stiffer springs than the one on a car? Of course. They hold trucks and cranes and trains. Holy nightmare, those are serious ones, right? So the spring constant K is the one that gives us the stiffness. So now, if I'm going to have the spring to do the work, so let's say we have a system where you have the spring like this attached to a crate. There you go, crate, right? The crate from position A and push it, let's say, to position B. That's the amount of push, right? The force that pushes is the force of the spring. Remember, the crate is now compressed, right? And then the spring is going to release and shoot this crate, certain distance apart. Now, this is something that you can easily try at home. That could take a little something, I don't know, attach it to the pen, spring, and then let go one end, and it will push it a little bit, right? So now, we can combine the two formulas and come up with the formula for work done by spring. So, work is equal to the integral a to b of kx dx, right? And then I'm just going to say, I'm going to put this in a box, and I will say work done by spring. Work done by the spring. So if the spring is compressed, when you let go, spring will push the object away, and if the spring is stretched with the object, you let go of the object, the spring will pull it back in, right? So that's the work done by spring. And again, why is this a function here? It's because, remember, it's the force that the spring is going to use is not going to be uniform. Everything in the world has to overcome that initial shock of the load, and then it equals out. The trains are designed in a particular way. The horses felt that for years. It's always that initial push or pull or whatever it is, and then after that it can stabilize, and then if it's biological system, it will start getting tired over time. I don't care whether it's 5 minutes or 1 hour. That depends on your physical conditioning or a horse's physical conditioning. But if it's electromotor or something that is electronic, it will probably keep constant force after that. But there you at least have that, first. So it's variable force. Okay, so now we can take a look at the problem for this. And the situation that you guys have to worry about is the situation where you are going to have the equilibrium state, and then that equilibrium state will go in two ways. There is the state from A to B, where it's pushing, right? And then the state from A to negative B, right, if it goes the other way. So we have, two-way situation, and you have to be careful. So A is the position where the spring is not bothered in any way, which is called equilibrium position. So that's where the A is. And then you have two states, state B and state negative B. When you have a spring that it's relaxed, it's in equilibrium position, right? You can either compress it or you can stretch it. And that's where the negative B limit and the positive B limit come in. So that's the part of Calc 2 you're learning. Integration is going to be basic Calc 1 again. So let's say, let's make up a problem. Say 40 newtons is required to stretch the spring whatever 0.1 meters. 0.1 meters is 10 centimeters, which is about the width of your hand. So 40 newtons is required to stretch the spring 0.1 meters. And then we're going to come up with few problems here. Part A, find K. Part B, how much work is done by spring to compress 0.3 meters. And let's go part C. How much additional work is required to stretch the spring from 0.1 meter to 0.4 meters. So we have these three questions. Clearly, in order to answer parts B and C, we have to answer part A first, because part A contains K, which is what we need for the red formula up there, so we can set up the rest of the problem. Now, what we have seen in the Hooke's law is that the force is equal to K times X. They say that the 40 newtons is going to stretch the spring 0.1 meter. So we are going to plug in the force of 40, and we are going to plug in X distance, 0.1. So when I multiply both sides, when I divide both sides by 0.1, I get K equals 400 newtons divided by meter. When I divide both sides, so over here I'll just say divide by 0.1. So 0.1, 0.1 will cancel on the right. 40 divided by 1 over 10 is 400. So we have that the K is 400. People who work with springs every day, they know exactly what that stiffness is and what applications that stiffness can be used for. So now we're going to part B. You want to compress the spring, right, to 0.3. All right, so work is equal to your spring was happy at 0. Its equilibrium point, and the spring is happy there. Then you come in and you bother it. Now, how do you bother the spring? You compress the spring, and it's going to, because you're compressing, you are going to go to the negative B side, right? So it's going to be negative 0.3. Did I say 0. Yeah, 0.3. You have your 400K times X dx, because the formula for the spring, as we have seen, is integral of kx dx. Now you have K as 400. And this will calculate the work that it takes for you to compress the spring 0.3 meters inward. So now you have your 400x squared over 2 computed from 0 to negative 0.3. This is 200x computed from 0 to negative 0.3. The square will kill the negative, right? So we have 200 times 0.3, it's negative 0.3 squared. So this is 200 times 0.09, which gives you 18 Newton meters. So the work of 18 Newton meters is required to compress the spring 0.3 meters. Part C is additional work required. So your spring is already stretched to 0.1 if you look at the text of the problem. And you are going additional length and you just want to calculate how much additional work is needed for this particular system. So you are already at 0.1, and then you want to bother it even more. So now you want to push it all the way to 0.4, and you still have your 400x dx. So technically, the only thing that you have to be very careful with here are the limits of integration. That's the only thing that changes, right? Once you have your k, it's always kx inside the integral. And it's always easy integration, right? Kx squared over 2. So the only thing is that you have to be careful which way the limits work out. Remember that the bottom limit is always the initial state of the spring. So whether it's already stretched or in equilibrium, if it's equilibrium, it's 0. The top limit is the one that it's a second state. So that whether you compressed it with a negative value or stretched it for the positive value. So now we integrate this. We're going to have the same 200x squared computed from 0.1 to 0.4. And that is going to be 200 and then 0.4 squared minus 0.1 squared is 200. This squared is 0.16 minus 0.01. That's going to be 200 times 0.15. And the whole thing is 30 Newton meters. So it needs 30 Newton meters to calculate. The way I'm calculating these things is you have two decimals over here, you have two zeros over here, they knock each other out. You just have 2 times 15 is 30. And that's the story of springs, right? That's it. You are remembering the formula of the spring, work done by spring, which is integral of kx dx. And then just have to be careful with limits. So work that out with the wording you have, whether you're going additional, whether you're going starting from 0 and stretching, compressing. So that's with a positive b, negative b. If you need to write that, if the picture over here is not enough, that's okay. Go on a side and say your a is always on the bottom, and it's either a 0 if it's equilibrium point, or if it's previously stretched or shrunk, it's going to be the value at which it is. And then B is the second stretch, a second state, whether it's a stretch or shrink. If you stretch it out, it's going to be positive B. If you compress it in, it's going to be negative value for what they pushed. And that's it. Yes?
So work is always going to be positive?
Not necessarily, because you get the work back as well, right? Depends on the reference point. So the answer to your question is yes, but also is no because of the reference point. In this case, it should be always positive because the way we define it. Now in physics, the Hooke's law is defined as negative kx because the spring always wants to do the opposite of what you are doing to it. Something like SJWs. All right. So that's the spring, and we have two more. The next one is going to be on lifting problems. Lifting problems are where you lift stuff off of the ground or the desk or whatever. You lifted your bag with your stuff to come here, right? You lifted your car keys. So lifting problems. So what is going on with lifting problems? Well, first of all, there are two different types of lifting that are there. And you might not consider them all, right? Both. Clearly lifting a single object in one shot. This is what you do all the time. But there is also the lifting of the objects where you don't pick them up in one shot. Think of that having a chain on the ground and you start picking up the chain. See, the most of the chain is still on the ground. You're maybe holding 10 links out of 100. What is happening if you're lifting more and more chain? It's getting heavier because you are adding extra links that are made out of metal, which is mass, which is, right? Or a person, right? Your friend is passed out next to you, right? Because you have had one too many, right? Lifting the whole person versus lifting just the torso up, right? So the rest of the person is still on the ground. Lifting just the torso to prop the person up is less work than lifting the entire unconscious person up, right? So when you have the lifting, we do not care much about easy problems, which are how much work is done to lift an object that you lift in one shot. There is no, as I'm lifting this roll of paper here, there is no part of it will remain to be lifted later in time. Like all one shot, done, right? But the chain has a different story, right? The chain is going to be taking its time, right? And as we said, the more you lift, the more stuff, the heavier it is, right? And the more stuff you have to hold. So the work is piling up and it's growing. It's not a constant number, it's growing. So we need integral for something like that. So if you have to beat and lift just a basic object like this, you use the basic formula for potential energy, which is mgy. Mgy, that's the formula in physics. You are lifting a massive object or an easy object, you're looking at as a mass, right? And then the gravity, well, are you lifting that stuff on the Earth or are you lifting that stuff on the moon? See, one of the issues that we have, right, with Mars is that the gravity of Mars is less than the gravity of Earth. You will be able to lift a whole bunch more on Mars because there is less gravity pull. You can jump higher, you can jump further, right? All of these kind of things. The issue is 20 generations down the line of people born on Mars, when generation of kids is born and generation next one and the next one and the next one and the next one, and those people that are born on Mars are making new generation of people, right? 20 generations down the line, they evolve to the point where their bone density and the stuff is not strong enough to withstand the Earth's higher gravity. Because if you don't need this build to survive the environment and gravity you're in, you're going to adjust to the one because, again, you just want to develop as much as needed to survive, right? So if any one of those come here, that kills. Literally, that shatters, the skull shatters every bone like this, right? Which now you understand why Superman is so damn strong on Earth, right? So the weight, and then obviously you have Y, which is how far you're lifting, right? That the higher you lift, the more work and more energy you need to invest in it. Why are there nets around all of the, huge buildings that you can visit the building top? What are they collecting? People?
Suicidal
No. There are bars with spikes and things to prevent from that. Why are they so fine? They're really, really fine, those nets. Really fine mesh. Why? What are they collecting?
People throw coins off.
Coins off, yes. What happens with a coin when you throw it from that height? It picks up so much energy, it becomes like a bullet hitting down. You take a penny and you toss it off the Empire State Building, it is going to go through the skull like that every time. Every time. That's what they're collecting. They're collecting coins, they're collecting little stones, they're collecting anything other than a piece of paper that you would throw off of the roof because you're an idiot. All right? The building that is very high is going to build up a lot of energy. The coin is going to hit the terminal velocity and so on, but it's enough to push through the skull. You can do those calculations. You have the formula. Again, so coin is not a big deal for us in this case for this problem. We want to lift the chain. So if you have anything that you have to pick up, measure its mass. You have the gravity, 9.1 for the metric system, 32.2 for feet per second squared, imperial units. 9.81 meters per second squared.
Oh.
That's the gravity measured in metric. They're generally rounded to 10, 9.81, but it varies also with the height and so on. So the gravity would be measured as 9.81 meters per second squared is unit, or G equals 32.2 feet per second squared if you want imperial. Those are the two numbers that you should know because that's the constant of this planet. Right? When someone mentions gravity, acceleration of gravity, you know what it is. So you will be accelerating if you jump off of the plane, right? Before you open the parachute, this is the acceleration that you are experiencing. So your plane had the 0 vertical acceleration because it goes across, and when you jump, right, you're starting with a 0 y velocity. When you jump out, you will be picking up velocity according to 9.81. Anyway, or 32.2, whatever one you want. So now we want the formula to deal with the problems of lifting the chain or a rope or part of the person with another, lifting more and more and more of a person as you are. So anything that would stay on a ground for some time as you are lifting. So chain is going to have a whole bunch of these links, right, that you lift, and it's going to have a whole bunch of stuff on the ground still, right? So this chain is going to go up in Y. So what's the formula for work? Formula for work is going to be the integral of rho g L minus y dy from 0 to L, which is the length of the chain. Now I have to explain this formula a little bit. We're going to put a box around it. Obviously there is no x version of this formula because you're not lifting anything in x direction, clearly. I need you to stare at the two formulas at the same time and realize that over here you have your mass, right? And over here you have density rho dy. That's mass, right? We learned the first formula we learned was rho dx, was mass. So now you have rho dy, that's mass of the chain. Gravity is gravity, great. And then you have your height y. Now look what you have over there. You have L minus y. Why is it L minus y? Well, if the chain is 2 meters tall, my height, right? If the chain is 2 meters tall, well, I'm not exactly 2, I'm almost 2. Then you will lift, 10 centimeters first, and then 20, and then 30, and then half a meter, and then, meter, and so on. So this y is measuring how much you lifted, and then L is the length of the chain. See, so it's a difference between the two. So it's exactly how much you hold, right? L minus y. And you are lifting the entire chain, the length of the chain, 0 to L. So I'm just going to say chain 0 to L length. Length of the entire chain. Maybe someone says lift half of the chain only. Okay, then the length of the chain is half, so you just calculate half, L over 2, right? So you can calculate the whole thing or the part of the thing. And that would be that formula. So let's take a look if we can find the problem. Oh, there is a shock absorber for the car. Heavy-duty shock absorber is compressed 2 centimeters equilibrium. So this can be something that you can work out with the car. Oh, this is the... Okay, whatever. So we can lift. Let's lift. I'm going to make up a problem. Lift 2-meter chain. Lift 2-meter chain. That's what the boss said at work. You want to calculate the work so you can be paid. So what's the work? What's the work done? Okay, so here we go. Work done is 0 to 2 rho g 2 minus y dy. That's the only thing you plug in. Now, rho. Rho is either given to you in the problem, or you know what the chain is made out of, and you go and look the property of that metal to figure out its density. So, rho for metal is different than the rho for plastic. The metal, the rho is different for gold, different for iron, different for steel, right? So, the reason why I don't have this is because I don't know those values, right? I'm not material sciences. The rho can be made out of plastic. It's going to have a different density rho, right? Since I don't have rho, I'm not even going to bother with G either, because that's the known constant that we can replace. So the property of the material that the chain is made out of will be given by rho, and that is in charts, right? Your physics book will have a chart which will say iron chain, steel chain, plastic chain, right? You can make chain out of pretty much anything you want, right? And that will be given in a chart. You will look at the value, I don't know, it's 13 or whatever, and you will replace rho with 13. And then gravity, since we are using 2 meters for the length of this, you will have to use 9.81, unless your professor says it's okay to round it to 10. Fine, why not? In our case, I'm not going to plug any of those two constants in, so I'm just going to kick them out, rho g, in front of the integral, and just integrate 2y minus y squared over 2, calculated from 0 to 2. And rho g, I have 4 minus 4 halves, gives me 2 rho g Newton meters in this case. Again, I go to the chart, I look at the chart, and whatever the chain is made out of, I know the rho because the chart will tell me the number. And then I know gravity is 9.8. I plug those two numbers in there, multiply by 2, and I actually have the work done in Newton meters to lift the chain. So all of the lift problems, whether it's a chain or a rope or whatever it is, right, will be using this particular formula. One more part of this lecture, and we're going to call it quits for chapter 6. And these are pumping problems. Let's say, unfortunately, basement flooded. Need to pump the water out. Maybe there is a pool. You have to pump the water out. If you leave it over the winter, tons of problems. Number one, what happens with ice when it forms? Yeah, it expands. What expanding ice in the pool is going to do? It's going to rip the pool apart, exactly. Whether it's a concrete or the above ground, I don't care what it is. If you do not drain the pool, you leave the water inside, when it freezes, your pool is done. It's history. And it's going to break the concrete, it's going to break whatever, right? So you have to drain it. You have to do the work to drain it. How much work? Well, you can calculate that. Well, obviously all of this is already calculated for you by engineers, but I'm just giving you an example of where these calculations came in handy at one point in life. So they say if you have the pool of this size, you have to buy this particular motor, this is of this horsepower, right? Whether it's a half horsepower, a quarter of horsepower, a third. Sub pumps for basements have the same rating. All of that is computed from engineers because the different horsepower is the different price for the pump, different design, and all of that kind of stuff. So someone at some point in life computed the work done so that they can figure out what amount of power is needed to push that out. And power has the energy times time and so on. So that's your horsepower for the car and so on. Have you ever had, next time someone brags to you that they have a horse or something because that's, I don't know why, important in today's day and age, remind them how much horsepower your car has. I had this when I was in the place, can't remember, something with Rotary. And there was this one said, yeah, I have a horse. I said, great, my horsepower in my car is about 250, so I have 250 horses, how about that? Like you think you're special with one. So there you go. And I don't have to feed it, I just put a little bit of gas, it costs $40. It's not a big deal, right? So you can calculate the work of pumping the water outside. Now, in a lot of industry, you might have tanks underground. Oh, gas stations. Did I mention gas, right? Gas station would have tanks underground, right? All of the gasoline is in the tanks underground. And those pumps where you park, right, with the nozzle, they have to pump the gas from under the ground, right, through the hose into your car. So there has to be a motorized pump somewhere that pumps the gas. So at some point in life, someone had to compute the amount of work done by pump, and those are the exact problems that we are going to do here. So we are going to take a look at the cheapest problem first, and then we're going to spice it up. We're going to take a look at the... That was a nice one. We're going to have a cylindrical, think of a Coke can or something, cylindrical, see, no one ever says Pepsi can, everyone says Coke can, right?
Because Coke tastes so much better.
Yeah, there are those arguments over there. I know, it's amazing, right? I don't drink either, but anyway,
You're
so...
missing out on so much. I said...
You just go for a neutral vintage.
So we have a tank that it's, let's say, underground, and it contains, let's say, gasoline, right? And that tank is going to have the hole on the bottom, and there is going to be a hose attached to it, or some kind of pipe that it's going to take the gasoline up to the surface. So we are going to say that this particular tank is, let's say, okay, I'm just going to make numbers up that they're not going to make sense, okay? I'm just going to put 10 meters tall and 2 meters radius of the tank, and the nozzle is going to, let's say, be at 15 meters. Because, guys, yeah, I understand that the ground is going to go somewhere over here, right? That's where the ground is. We have to set the reference point for our calculations where it's easiest for us. And that's going to be the bottom of the tank. So we are setting our reference point here. For all measurements. Reference points for the height of the tank, reference point for the height at which you have to pump whatever you're pumping under the ground. So now you want to, obviously you are scooping from the bottom, because as you the straw, even if you drink with a straw, it goes all the way to the bottom. So as you are taking the liquid, the gravity will be pushing the remaining of the water to be on the bottom always, right? So let's say we have water or gas or whatever it is up to level, let's say over here, level 6. So all of this is filled. So let's call this level 6 right there. And if I have the level 6 over here, I'm going to have up to level 6 the liquid inside this nozzle, which is what I get for free, thanks to gravity. It's called Archimedes' principle in physics and so on. There's more physics. There's always more physics that you can add to all of this stuff. So now, this is what we have as a setup. The blue liquid can be whatever you want it to be, water, gasoline, I don't care, right? So now, what are we doing? Well, we are going to write a formula which will have all of these features in there. And the formula will give us the work done, where we have integral from A to B. Now that A to B is a little bit trickier than for the rest of the ones. We'll see that. We have our rho G again. See, rho is going to be the density of the liquid. I know for water it's 1,000. That's the in metric unit.
Just one.
Well, depends on which one. Yeah. Is it going to be kilograms or grams? You're right. So it's 1 or 1,000. Depends on which units you use. Because kilogram and gram are 1,000 units apart. So you can have them either in kilograms or in... So, okay, 1 or 1,000. Gravity, we all know, 9.81. We talked about it. So now, here are the new features. New feature over here is A of y. And then you still have your good old L minus y, and you have a dy. So the new feature that is added, in addition to the previous formula we had, is this A of y. And yes.
Why aren't you using H instead of L?
To match the notation in the book, to be honest, I can care less what you use. H is for height, and I would agree 100%. So if you like, use H, it's fine. I will understand it. So if you want to, I'm just matching the notation they have in the book, so it's not confusing that I'm giving a different formula. All right, guys, so if you take this A of y out, you're lifting the chain, right? Now, see, the trick over here with the liquid is that the liquid fills the area. You see that blue circle on top, right? That circle is actually the cross-section area of your tank, and it's going to play a role. You see, in this case, when you have the cylinder, right, that A is constant. If you are to use a cone, that A would be changing. Because let's say you put a cone that has the spike down, right? Then the liquid on top, the top portion of the liquid, because it's a cone, it will keep getting smaller and smaller and smaller and smaller and smaller, right? So it depends on the shape of the tank, and the shape of the tank is taken into consideration through A of Y, meaning cross-sectional area in respect to the height at which you are looking at that area, because it's A of Y, right? And the Y measures the vertical distances. So now the L minus Y is the nozzle. So I have to now give you all of these specs over here. So A to A, amount of liquid we pump. A is the area, and L minus Y, height to which we pump. So to set up this particular problem, I am going to have a volume is equal to, and now my question is, do you want to pump out everything? No? How much do you want to pump out? You want to pump out half? Great. Half of that, you have 6 meters of liquid inside. You are pumping out half of that, which means 3. What are my limits on the integral? Because that's the amount of liquid pumped out.
It would be 6 and then the negative 3.
Technically, this is the state 1. After the 3 meters of liquid are pumped out, what is going to be there?
3.
Which 3? Are going to be 0 to 3 or 3 to 6? 0 to 3, right? So which one are you pumping out? You are pumping out 3 to 6, exactly. You see? So if you want to pump out 3 meters of liquid, please, the 3 meters of liquid that you are eliminating over here are the top 3, right? So that's the reason why the limits are 3 to 6. Because if you are to come back and, let's say an hour later, the only thing that stays in the tank is 0 to 3. So now you have 0 to 6. When you pump out half, you are pumping 3 meters out, but you are pumping 3 to 6 out. So that's one of the common mistakes, that if you put your limits to be 0 to 3 because you are pumping 3 out, then what? This 3 to 6 is going to levitate in there over the empty space in the bottom, right? So you have to, use the appropriate limits. Here's our rho G. Again, we know the gravity, and the rho, what is this? Water, gasoline, blood, whatever it is. Now, A of Y. Well, this is a circle which will have pi r squared. So pi times 4, right? Pi r squared is this one. And I said we're pumping it up to 15, so 15 minus y, because I said the nozzle is up at 15. If you take a look at the picture, right here, it says 15 meters. So I'm pumping it up to 15 meters height. And that's where the 15 goes. So the limits deal with the amount of water in a tank, and the L at the end over there deals with how high up you go to push it out. So this is what you see there is the cheapest problem that you can possibly have for the pumping problems. Anything you change, obviously it's going to get spicier. Yes?
When we're doing gravity, we're not using negative.
No, we because we see energy. you pour energy into system, you take the energy out of the system, right? But it's the same amount of energy. So if you are pumping, we all know that you need to put the energy into the system to move this liquid up, right? So we're looking for the positive answer anyway. You get a negative answer, you put the absolute value around it. We don't have to worry about physics. Uses a lot of negative signs here and there, like I said about Hooke's law and so on. And the reason is the reference point, and then you go up or you go down. So it has a direction. And in math, we just care about the number, and then you can reason which way it goes. So that's the reason why we don't worry about negative G. For radius squared, that's the area, cross-section area. It's a circle, right? R squared pi. Let me just actually do this and I say r squared pi. Maybe I should put, I'm going to put 4 pi because I see a lot of you are writing with pens, so now you have scratched off. It wouldn't be a day if I wasn't a pest for at least like 2 seconds. Okay, so and we calculate this now. So we have 4 pi rho g. That's all kicked out. It's all constants. You integrate your 15, you get 15y minus y squared over 2, computed from 3 to 6. All of that is equal to a number, and there you go, done. Cool, huh? Of course, it's math. So let's take a look at the conical tank. Because obviously you're going to go for this design because you can hammer it easier into ground. And if you didn't like that analogy, then fine. You might want to pump the ice cream out of the melted ice cream in the cone. The bottom has a nozzle right there, a hole. And you're pumping that ice cream up, from the cone. Exactly 1 inch above. All right, so here's the conical tank now, and this one is going to be much trickier. What's the radius over here? You pick numbers.
3.
The radius is 3, okay. And what's the height of the cone?
3.
3, fine. How much liquid do we have inside? Okay. You can, because it's full. It's okay. It's all perfect. It's full. Full. How tall is the nozzle? And it can't be 3.
18.
Holy night. Okay, 18. Fine. You win. So, 3 meters, 3 meters, 18 meters, full of water inside. Great. Do you want to pump everything out or a little bit? Remember, you have 0 to 3 to play with.
Just 1.
You pump out 1. Pump out 1 meter. So you know immediately what your limits are, right? What are your limits? 2 to 3. 2 to 3. Because you're pumping only 1. Great. Well, the issue is AOY. You see that it's not constant anymore? Your area used to be r squared pi because every circle had the same radius, but now radius changes as the liquid starts going down. And we have to capture that change and express the radius r in terms of y. And for that, we are going to use our famous similar triangle method you guys learned in, I believe, related rates in Calc 1. So when you have a cone, if you cut it for this, you're going to get this triangle here, and then you say there is the height, unknown height r. You know that this one is 3. You know that the big one is 3 over here, right? So I'm tempted to change that 3 actually because you're going to see this better if I change this 3 to anything else bigger than 3.
6.
6. We are changing the height of the cone to 6 so that the proportion formula is not with 2 trees and you don't know which one came from where, right? I have the height of the liquid measured as y. If you want the age, go ahead, that's fine. So I have the height of the liquid measured as y. I have the radius, which keeps changing. The less liquid you have, the smaller the radius in this case. And I can write the proportion, what 3 is to r, 6 is to y. And this is the formula that links our r to y, and then I can stuff that into the area equation, square it and be done. So you have that 3y is equal to 6r, from where y, no, you have to change the r. R is equal to y over 2. So now, since your area is r squared pi, the area in terms of y is going to be y over 2 squared pi. So you are replacing the r's with what r's are in terms of y. And that depends only on the ratio height to the radius of the cone. You can change these numbers for the cone. Immediately it will change the relationship between r and the y.
How do we know that relationship is true?
Similar triangles, geometry. Because you have the big triangle over here. That's the big triangle. And then you have the small triangle here. They share the same side over here, and these two are parallel. That says similar triangles, and if you have similar triangles, you can write the proportion. So now, I have my A of y, and that A of y, when I work it out, is going to be pi over 2 y squared. No, pi over 4, I lied. Pi over 4 y squared, when you work it out. So now I have my A of y, and you can see that it changes in respect to y, so wherever the liquid gets to be. So I have all of the ingredients for the soup. Let's make the soup.
Isn't it supposed to be 1/3 pi radius squared height for cone?
Yeah, but we're not looking for volume. What you said is 100% correct for a different topic. Because that is the volume of the cone, yes. So now we just need the area of the circle. So I have my limits 2 to 3 because we are only pumping out 1 meter of liquid.
Is it 2 to 6 now?
Wouldn't it be?
Oh yes, it would be 5 to 6 because you want, yes, it's 5 to 6, thank you. Because we changed the height, I changed the height. So it is 5 to 6. Oh, that escaped me totally. Excellent. See, I was testing you all, and right? Very good. All right, so what do we have? We have our rho g, the density, what kind of liquid, and the gravity. And now we have our area, which is pi over 4 y squared. And then we have the 18 minus y. The height of the nozzle is all the way up at 18. What are the constants? Well, pi over 4 rho g goes outside. Those are all numbers. And now I have to, for integration, I have to distribute y squared. So I have 18y squared minus y cubed dy. And now we can integrate each one of these. That's pi over 4 rho g. 18 divided by 3 is going to be 6y cubed minus y to the 4 over 4, computed from 5 to 6. Right? Because y squared is going to be y cubed over 3. 18 divided by 3 is 6, so 6y cubed. And now we can plug these values in. Remember, the upper limit minus the lower limit. So we have 6 times 6 cubed minus 6 to the 4th over 4 minus 6 times 5 cubed plus, because minus and minus will give plus, 5 to the 4 over 4. And all of that is equal to a number it's easy to compute this number because over here you have 6 times 6 cubed, that's 6 to the 4th. So 6 to the 4th and 6 to the 4th, you can factor it out, you get 3/4 there. And then can factor out 5 to the 3, which is 125 over there, you get -6. 5/4 minus -6. So it can be computed easily, but yeah. You can also punch it in a calculator. So, as I looked at the book, their measurements for the same cone I just did, we have 6x3, they have 6x1.5. So it's the same question given in the homework. Now, are all of these problems as cheap as cone and no. They get to be really tricky. If you want challenge, go look for spherical tanks. Look for the pool that has uneven bottom, right? Because remember, if you have a pool that constantly gets deeper, the bottom of the pool is on the slope. So whenever the shallowest end was, let's say it was 2 feet, right? That 2 feet on top is just a box that you can, right, it's easy. It's the one on the bottom that creates a triangle on the side whose area changes with the height of the water. When you look at the top of the pool, right, you look at the top of the pool, when that slope is, when you start filling water or taking the water out, it's always a rectangle, but that rectangle gets bigger or smaller because the pool is on the slope like this. So when I fill the water in here, it's going to create a rectangle like that, right? And then the water is higher, the rectangle is bigger. Over here, rectangle is very small. So it's an awesome problem. When I was a kid, they used to take me to the village where my grandma's family is from. Still have family in the same village. I can't wait to go back. Actually, it's really awesome. It's the time for me to see the animals and things and eat like the best food in the galaxy.
Where's that?
In Serbia. Virovac. It's an awesome place. To feed animals or to feed animals or to give them water or something, you can take a barrel, just like the one that we had, and you cut it vertically, and when you open it up, you have two halves, what are called troughs, exactly. So you have a trough like this, and then they have this shape. And now, when you fill it, let's say with water, let's say you want to drain this and you want to do calculus, right? That problem is not as easy as the ones you had before, because if you have your water here on this level and you lose some water, even though this face over here, well, it's going to be like that actually, this always is a rectangle.
How?
When you look from the top, it's a rectangle, right?
Oh, from the top.
Yeah, you look from the top, it's a rectangle.
Uh-huh.
But when the water goes down, that rectangle gets shorter here. It's the same length. You know, let's say length is 10 feet. Fine. But it gets shorter there. To find the area of the rectangle, it's length times width. Well, the length is always 10 feet. So it's, how do you model this one? To drop down with the height.
Isn't that the radius minus the height of the water?
For a quarter circle, you just calculate a quarter circle and it changes it gets shorter because the radius closes in on it.
Unfortunately, no, it's much worse than both of those.
Do a parabola?
Nope, it's a half a circle. Not a problem. So you know, if you, I kind of don't want to kill it now and show. This is advanced problem. Do you want to spend some time and try to figure it out? I'm telling you, it's a half circle over there. I already told you what you should know, right? It's rectangle on top. And if I give you some units over here, let's say from here to here is 2. I'm gonna do that in black. I'm gonna give the whole units actually. So from here to here is 4 meters, let's say, and the length of the whole thing, let's go 10 meters. This is huge. I mean, those are terrible units for I don't know, maybe you have some chemical plant that needs this outside, right? I don't care. I gave you the dimensions that you would get as an engineer that is developing this pool. You need to know the work done to pump the chemical out. This is your design job, to design a factory setting for a chemical plant of some kind. I don't care what it is, right? They need to know the work done so they can either design or buy a particular motor of particular strength, which is the motor runs the pump, right? And the strength of the motor will also tell you in how fast and you can, right? Because can you take any motor, any pump and drain this? Yeah, but some of them will take a year and others will take 30 minutes, right? So I need to know how much work is done to pump out the water from here. Now, as I said, this is not something that you go home today and you say, I'm gonna solve this, I'm gonna be the cool kid next time. No, you gotta go and you gotta learn, you gotta do another 5 or 10 problems before you tackle this one. Not a joke. And I can, work with you guys. You cannot, there will be no proportions and things like that.
Well, if we're doing this for like pumping it out, do we need a end height where we're actually pumping from?
You can pump it 20, you can make that up to 20. Let's set it up. So what height do you want to pump it up to?
23.
You come up with these arbitrary numbers, man. Okay, fine.
We'll run out of fluid before it reaches the pump.
Yeah. Pump out to 23. It doesn't matter. All right. You can literally put any number you want. You want 23, 23 it is. And my pen stops working now. There we go. 23 meters, fine.
So the
You
width,
could have said 1 or 3 or 4.
the width of the column doesn't matter at all for the amount of work that a pump would have to do?
It does, but not to the.
Like if we have a column that's like 6 meters wide, it would be a lot more work for a pump to push
Yeah.
Of course, but
than if it was like
those specifications come with the pump, and again, first of all, why would you do that? Second, right, to have a 6 feet column over here, right, to pump something up,
Well, maybe
you
not.
are probably pumping a lake out,
No,
okay?
yeah, exactly.
But for these purposes, you're just using the regular, garden hose, let's say, or something. So it's not gonna be, you can have a 1-inch pipe or those things are not gonna. Again, they work with the pump. Pump has. You are not going to get a pump that has a quarter diameter for the hose, and then you're going to put a converter that's going to put it out to 2 inches, because there's going to be a restriction right there. So that's already in the design of the pump, so that's why we don't have to worry about that part.
Okay.
Right? It's worked out with a pump. It works only one way. Well, guys, that's physics. There's more in this lecture than this. I believe maybe even other 2 concepts. But we're going to stop here, take a break. When we come back, chapter 7, 7.1.
What's the name of that chapter?